Okay. Good afternoon, dear students. Today we start the next lecture on, and that is on hypothesis and error analysis. So this is the sequence of the lectures that we have been discussing, and today we'll discuss some of the examples of testing of hypothesis and also the general aspects of analysis of data, interpreting the results, and also accuracy and precision of our measurements. So this will be the topic for today's discussion. First, we will discuss the testing of the hypothesis. So I have some examples. Through these examples, I will bring home the point that how you have to draw conclusions about testing of a hypothesis. Before I begin my lecture, I had to make one announcement. In the chat box, you will be given a Google form link wherein you are required to enter your name. You have to open that link, Google form link, and enter your name, email ID, mobile number, enrollment number, and name of the CIOCC. So I repeat again, in the chat box today, you will be given a Google form link wherein you have to click that link and enter your name, email address, mobile number, enrollment number, and the name of your CI or OCC. And this is required to make a list of all the students CI wise, because this will be important for the evaluation of assignments and conducting the examination. So you have 2 days time, today and tomorrow. You can fill that Google form link and submit it there so that we have the complete data about all the students. I will announce it again at the end, but I know many of the students are still not joined yet. So hopefully I'll be announcing this again at the end of my lecture. But if you happen to know some friends who are still not joined, will be joining, you can inform them so that they know what they have to do. Okay. So today we start the discussion on how to interpret the results when we are testing a hypothesis. And I have taken some examples from the book by Marder. So this is an example of a study to study the effect of lubricant on the descent time of a ball on the ramp. So just I have given a cartoon here, like it's like a slide, a slide is there and you are rolling a ball from here to here. So you can put optical sensors to record the start time of the ball and the stop time of the ball. And so that every time the distance traveled is same. So you note down the time. Okay, this is the experiment. And then after you, let us say you have done 10 measurements on recording the time of descent from start to stop, then you lubricate this channel. And after that lubrication, again, you repeat the experiment with the ball and note down the descent time. So that is the experiment. And what you see here, that the descent time in unlubricated channel in seconds, these are the 10 readings that were measured in an experiment. And then it was repeated after lubricating the channels. So you have this another 10 readings. Now you can see visually, you will see they are very close. So from here, you cannot make out whether the lubrication had an effect on the descent time of the ball or not. So that is why you require the statistical analysis of the data. So you have a null hypothesis. The null hypothesis says that the lubricant has no effect on the rolling time of the ball. So you expect that they should be giving the same results. There should be no any significant difference between the two. So if you do the analysis of this data, what you need to do, you find out the number of measurements is 10 for each case. and then you determine the average of the descent time. So for the unlubricated, this is the time, this is the mean value 0.304, and the standard deviation is 0.013, and then this standard error of mean, that means standard deviation divided by root of number of measurements, is 0.004. So similarly, you do the exercise for the lubricated case, and you find the value, mean value 0.324, standard deviation 0.018, and the standard error of mean 0.006. You can also plot the data as a function of for the data on descent average value, mean values, and the standard deviation for the lubricated and unlubricated. And you can see here, they say this is the advantage of putting the error bars, So this with error bars, they are not overlapping, so they look to be distinct. Means it appears that lubrication did have an effect on the rolling down time of the ball through the ram. So these are the data. Finally, unlubricated channel 0.304 plus minus 0.004, lubricated 0.324, 0.00. So it shows that lubricating the channel has a significant effect on the time needed for the ball to roll to this between these 2 points. But to be statistically true, you have to carry out an analysis of this data, and that the analysis is done here. So what you do is the t-test you do. If you recollect the previous lecture on Monday, the t-test, the t is the ratio between the difference between mean and expected mean, that is the true value and the sample mean, true mean and sample mean, and the standard error. So this is how you get the mean minus the population mean, sample mean minus population mean upon the standard error of mean, s by root n, or standard error you can write at delta x. But here there are 2 mean values measured experimentally. So here you can use this data. Both of them have their variances also. So for unequal variances, when you are comparing 2 measurement values, you can calculate t, like you take one of them as true value, other one is the sample value, and you can apply though. Let us say x, y are the 2 mean values, then x bar minus y bar upon the sum of the standard errors of means square root. So this is the t formula for in this particular case. You calculate t 0.30324 minus 0.304 upon square root of the 2 standard error values. So you get 2.77. Now you recollect we had the t table for depending upon the number of degrees of freedom and the confidence level. For the t values, you have the p, the probability values. So from that t table, it is noted down using a 2-sided test. That means 2 tails on both sides, assuming equal variances. You get the n for n equal to 10, t equal to 2.77. You get the probability equal to 0.014. Now this probability that above difference is due to chance alone is 0.014. Okay. Normally, if you want to, conventionally what you do, this value, if it is 0.05, that means at alpha value 0.05 at 95% confidence, if your p value is less than 0.05, you say that the difference is significant. So only you cannot explain it by chance alone. This is a significant difference between the 2 values. So in this particular case, what we are getting the p value much less than. So if you see that Gaussian distribution and you say alpha is 0.05, that 0.025 on left, 0.05 on the right side, then this value, p value corresponds to more than that in that shaded area of 0.025 alpha. That means by chance, it is not that by chance, the difference is significant. So this t-test confirms that the experiment has arrived at a significant result. It means there is a significant effect of lubrication on the rolling down of. So if the p-value has to be less than this p-value for that confidence level. So thus this way, what was the null hypothesis? That the lubrication has no effect on the descent time, but it does have an effect which we have proved statistically. So the null hypothesis has been rejected. And therefore, you can conclude that the lubrication has an effect on the rolling time of the ball. So this is how you have to do an exercise. And particularly when you draw conclusions out of whenever there are very small difference between the two values. So this is how you can go about doing the statistical analysis. This is another example. And I gave you this example in the early lectures where that there are two lakes, let us say A and B, and there is a small fish called three spines trickleback, which has got three spines on the back of it. Now lake A, which is a bigger lake, which has another fish called trout, and this trout fish preys on these sticklebacks. And so normally, one would expect that this in the lake A, where there is another, the predator is there, the sticklebacks may develop larger spines to ward off the trout. That is from the theory of evolution or adaptation of the species. You can predict that. So what you expect is that the spines on the sticklebacks of A lake should be larger than that of the B. This is the expectation, and this is the experiment. So the data were collected, and you can see several data are collected. So this is the length of the spines in the lake A in millimeters, and this is for the length of the spines in lake B in millimeters. And this number of data are not same; they are different. So bigger lake you may have more data and so on. So now this is the problem that you have to study, whether the stickleback fish in the lake A, they have significantly higher length of spines than that in the lake B. So you take a null hypothesis. Null hypothesis is that the spines on sticklebacks in the two lakes are of same size. That means there is no difference between the spine lengths in the two lakes. But if you analyze the data of the previous, the table which I showed here, then you calculate the mean. Mean is 4.92, the standard deviation is 0.76, and the standard error of mean 0.07 millimeter. For the lake B, 4.67, standard deviation 0.57, and the standard error 0.05 millimeter. So final result is XA 4.92 plus 0.07, XB 4.67 plus 0.05. So looking at the value, it appears that on the average, spines of sticklebacks in lake are larger than those. If you see the numbers, they look very similar. So here also you have something like 3.28, but here also you will have 5 point something. So all sorts of measurements are there. So from this data, you can say null hypothesis is rejected. Now from here you can say that the data appear to be, the lake A appear to have spines bigger than B, and this data also is plotted here. So lake A data is significantly higher than that of lake B. But if you want to statistically confirm this, you do a t-test. And here for unequal variance, you can again use this t value. So 4.92 by 4.67 upon the squares of the errors, so 4.90. And you read from the t table, the p value is 0.0056. Again, which is much less than the conventional threshold of p equal to 0.05 for 95% confidence. So this concludes that the results are significant. Means there is a significant difference between the mean spine lengths of the two lakes. So hence, the spines on the sticklebacks of A lake are significantly larger than that of B lake. So this is how you can quantitatively confirm the outcome of a study. There is one more example of flipping a coin. So now suppose you get a coin and you are going to toss it several times, and suppose you don't get half the number of times you get head, half the time normally you expect. But here you may suspect that the coin is biased. Coin has some problem. It preferentially goes in one direction, one side. So how to confirm that the coin is fair? So you make a null hypothesis that coin is fair. That means half the time it becomes head, half the time it becomes tails. So this is the data of 100 times you flip a coin and 1 equal to head, 0 equal to tails. These are the 100 data. So you will get either 0 or 1 depending upon whether you get tail or head. And then you analyze this data statistically to tell whether the coin is fair or not. Now, if you flip the coin infinite number of times, you will get P equal to 0.5. So half the time you get head, half the time you get tails. But in this particular case, what you get out of 100 flips, it is 46 times it is one way, 46 times it is head, and 54 times it is tail. So is it a fair? Based on this observation, according to this data, you may say that it is not fair. It is preferring to show one side. So the average of the flips you can calculate. 46 times you get head and 54 times tail divided by 100. So you get 0.46. Instead of 0.5, you get 0.46. And the standard deviation you can calculate from this because the mean value is 0.5. So you can calculate the standard deviation. Now, the standard error of mean you can calculate from that standard deviation value. So delta x s by root 100 is 0.05. So the final result is number of heads, probability of head 0.46 plus minus 0.05. Now, statistically, you see here plus 0.05 means 0.51. So this overlaps the expected value of 0.5. You can see here also, this is the expected value where there is no error bar shown. And this is the measured value. So 0.46 plus minus 0.05. So you see here, this error bar appears to overlap with this expected value. And so based on this outcome, you can say that the null hypothesis is not rejected. That means the coin is fair. Though you are getting 0.46 as the probability of head, mean value for the heads, the coin is still fair. So what you have to do? Probably you have to do it more times. So these are the kind of studies we need to do to test a hypothesis. Now, there are actually, during this hypothesis testing, you have in fact two types of errors that are appearing. They are called type 1 and type 2. So type 1 error is that null hypothesis is rejected even though it is correct. So when I told that the confidence level is 95%, you are 95% confident that null hypothesis is rejected, but you are still 5%, you are not sure. It is possible that 5% time it may be correct also. So that is called the false positive. Like, even you are testing the faulty, defective pieces in a factory, it is possible that it is detected as it is rejected, but actually it may not be defective. That is called the false positive. Now, very interesting example I'll give you. Linus Pauling in 1970 claimed that vitamin C prevents and alleviates the episodes of common cold. Now also, many times, when you are having common cold, you take vitamin C. And this happens when a big shot, the powerful person, very popular person makes a statement, people take it very seriously. And so people, in fact, now also people take vitamin C to prevent common cold. So this is the null hypothesis that vitamin C prevents a common cold. And subsequent to this claim by Pauling, there have been so many studies in very accurate measurements have been done to see whether vitamin C prevents common cold or not. And after decades of experimentation, it was found they could not find a connection between taking large doses of vitamin C and prevention of cold. So there is no connection between common cold and vitamin C preventing common cold, Still, millions of people take vitamin C in response to cold anyway. So this is called the polling effect, and it is a type 1 error. That means the vitamin C does not prevent common cold, but you take vitamin C thinking that yes, it will do it. So this is the kind of things happen out of these studies. There is another type of study. It's called type 2. Type 2 error means null hypothesis is accepted when it is false. That is called false negative. It is actually false, but you accept the null hypothesis. So the example is null hypothesis example: smoking causes lung cancer and heart disease. All of us know lung cancer and smoking leads to heart problem and lung cancer. Now, the connection between smoking and heart disease became too clear to deny it because it is everybody knows. But in what happened now in 1957, Sir Ronald Fisher, who is the father of modern statistics, and he was a chain smoker, he told that it is not this connection. You cannot say it is due to that. There is possible that people might be genetically disposed to develop these diseases and to smoke. So it may not be that smoking is causing lung cancer. People who may be genetically who are smoking, they may be genetically disposed to getting the heart problem and also to smoke. So it is not nothing to do with the smoking is causing lung cancer. That was his conjecture. So what the people did, they did the experiment on twins who are genetically related. And one of the twins is smoked and the other did not. And it was found that the twin who smoked had much higher rate of heart disease and lung cancer than the one who did not smoke. And this put the whole issue to rest. This is the study which confirmed that smoking does cause heart attack, heart disease, and lung cancer. So these are the kind of, so whenever a big person, makes a statement, you have to rule out or to nullify that, you have to really do a quantitative study. And so this kind of errors may creep in and you have to refute them or you have to confirm them by suitable experimentations. Okay. So this type 1 and type 2 errors actually creep in our when we are doing some measurements. So I'll come to some, when we do measurements, particularly when the signal is very weak and the background is also signal to noise ratios are very low. Many a times we are at a loss whether to conclude that there is some signal is there or not. And so for that, this type 1, type 2 errors become important. So the type 1 or false positive type of error means concluding that a substance is present when truly it is not. This is particularly relevant to the people who are involved in measurement of concentrations or some signals, So when we say type 1 error, that substance is present, but it is actually not. So you see here, suppose you are doing the measurement of background, then these are the data. That black line is the background error, background data. So this is the background data. The noise also will have a Gaussian distribution. And at alpha of 0.05, suppose it is a two-tailed function, then beyond in that alpha by 2, there may be some data which may be sitting here. So that will become a part of type 1 error. Whereas the false negative or type 2 error means concluding that a substance is not present, but actually it is there. That means, suppose it is a part of this. So this is the sample. The red one, it can be a sample. And significant part of this may overlap with the background. Now, the type B, the beta error, type 2 error means your sample, you may say sample it is not there present, but actually it is there. So a part of the sample distribution may overlap with this one background, and then you may say it contains it does not contain, but actually it contains. So this kind of confusions arise, and to clear that uncertainties, there are types of quantities defined called limit of detection and limit of quantification. So in terms of alpha, that means if a measurement gives you a value more than 3 times the blank standard deviation, you say you are 99% confident that this contains the substance, the quantity, the material that you are looking for is present. So you say 3 sigma of the blank gives the detection limit of detection. And then you see in the literature that that is for detection, that yes, you can detect it. But if you want to quantify, then if you get some data at 10 times the standard deviation of the blank, that is called the limit of quantification. So in fact, there are some, you will find different types of formulation with regard to limit of detection, limit of quantification. So this may not be true if you read some other paper. So to clear these doubts, I thought better to follow some standard literature. And for that, I have taken the data from this paper, L.A. Curry, Analytical Chemistry, Volume 40, 1968. So those of you who are really into the measurement of concentrations, very low concentrations, and want to make a thorough assessment of your measurements, this is the literature to read, and I have shared with you. You can go to that paper. It is available in the internet freely. So this is about the decision, detection, and determination levels. So again, I have shown you these two Gaussians, one due to the blank, other one due to the sample. So this is the alpha threshold. That means if you take alpha, depending upon the value of alpha, you can take alpha equal to 0.05, alpha 0.025, and so on. So if you recall the alpha in the Z statistics, depending upon the value of alpha, you have different Z value. So this is nothing but the Z value, or we call it K alpha. That means when we say 5% uncertainty, it is 1.64 sigma away. So this horizontal bar refers to 1.64 sigma of the background. Now, if you get a measurement more than mean background plus 1.96 times this value, then find the background, the standard deviation of the background, you say that it may contain the substance that you are analyzing. So that is called the decision level. But you are not sure. It's called unreliable detection. So this is called the critical level for detection. And only it is away from the mean of the background by K alpha sigma 0, where sigma 0 is the standard deviation of the background. Let's say you can say 1.96 sigma of background. This is the 5%, 95% confidence level. So if you get more than this, you say it is unreliable detection. So it is called the decision level. It is there, but you are not sure whether it is how to detect it. Then to be more sure, so what you do, you define the population, the distribution for the sample, and it is another level of confidence that this value you add to that the beta for the sample, you have the type 2 error. So K beta for this sample distribution into the standard deviation of the sample. So this also you can have the same table. You can take the K beta again here, assuming that the sigma D for the sample, the sigma is same as sigma for the blank. It can be taken because most of them, they are all random. So you can assume that sigma 0 and sigma D are same. So now the limit of detection for the sample is sum of the two values. This is what I tried to explain here, that the decision threshold, the decision that yes, your sample contains the signal, the impurity that you are looking for. So this is called the decision level. K alpha sigma 0 for alpha equal to 0.05, K is 1.96. So background plus 1.96 sigma, if that is present, then you say it is present. Detection threshold, to call detection limits. In analytical chemistry, detection limits are very widely used. And so detection limit is defined as K alpha sigma 0. This is the standard deviation of background plus K beta sigma D, standard deviation of the sample. And many times you will say that sigma 0 is same as sigma D. So that is K alpha plus K beta sigma 0. So if you take them as same, then 1.96 into 2, 3.92 times the sigma 0. So if you get a data more than 3.92 sigma of background, you say this is the detection limit. Detection for the, so qualitatively you can say you are able to detect the substance that you are looking for under the alpha beta equal to 0.05. Then there is the limit of quantification, or it called the determination threshold. So the determination threshold has been defined as 10 times the sigma 0. It is based on the KQ. The KQ is the 10 here, and the sigma Q again is the, you can say, again you can see sigma 0. You can take this as sigma 0. So the standard deviation for the measurement of for the signal background and sample can be assumed to be same. And so in that case, the limit of quantification becomes 10 sigma 0. So these are the kind of thresholds one can use in analytical chemistry, or many times you may be doing measurements of different type. Like for example, if you are determining the neutrino mass and you are very close to 0, how do you quantify? How do you are how confident you are, and what is the limit of your detection? So all that will require a statistical analysis of your data to tell whether you are able to determine the mass of neutrino or not. Like that, in any field of science, whenever you are doing a measurement and you want to define some limits for quantification, you can use this formulation for your work. Okay. So now I'll come to the accuracy and precision. As most of you may be knowing about this. Accuracy is the degree of closeness of a measured value, x bar, to its true value, mu. So we have discussed this thoroughly in the previous lecture, mu and x bar. So accuracy can be defined as x bar minus mu upon mu into 100. So this much percent is the, how close x bar is to the mean, true the mean population mean, you can say this is the percentage accuracy. Then another quantity is called the precision. Precision is the degree of closeness of all measured values among themselves, and it is quantified by the standard deviation, which you calculate by this formula. And you many times, to compare different measurement values, you say percentage RSD, relative standard deviation. So standard deviation upon x bar into 100 percentage. So these are the three quantities many times you will quote when you are doing some measurements. Just to give you some examples on how to handle the data. So when you finally report a number, it should reflect the accuracy and precision. And many times we do make mistakes in our theses. I have seen students mentioning so many digits, significant digits in the handle data. So a numerical result is very precise when it is specified to too many digits, or when the error bars surrounding it are very small. So you may get a data and you put, suppose you take some values a minus b, and you get c, and that c calculator gives you several digits. So you have to be very careful in reporting such number when you are using a computer or calculator to do the numbers. Just to give you an example. So you measure the mass of a coin in a balance in grams, and these are the 10 measurements of that coin mass, 2.532, 2.525, and so on. Now, if you want to arrive at a mean value of the mass of the coin, you get 2.5208. You take the mean value by a Excel sheet or calculator, and a standard deviation 0.00311898. Like that, you can get numbers, But whether they are correct or not, what decimal point you should take, that we should be knowing. So this data appear to be too precise. You see, up to 6th decimal point you are telling. So that means it is micrograms. 2 grams, 6th decimal will be micrograms. But your balance that you are weighing may be weighing only up to 1 milligram. Most of the digital balances, maximum 0.1 milligram and then 0.1 milligram value will be fluctuating. So it is quite misleading when you quote such numbers, because the weight of the coin is not known with that much accuracy. And you can say the accuracy with the result is actually known as 0.001 gram. Because normally, up to 1 milligram, you can say it is fairly accurate. So hence you have to use only up to that many decimal points. So the mass of the coin, you can say 2.529. You truncate, you round it off to third decimal point. And the standard deviation also. So you should have this many significant digits. So you write this value in terms of scientific notation, 3.11 e raised to e minus 0, 10 power minus 0.3. And the standard error of mean is s by root n. So it will be 9.87, 10 power minus 4. So that is how you have to report the data. You cannot write 0.00311 or 0.000987. So that is where the significant digits become very important. And so you need to show the appropriate number of significant digits, rounding of the data is very important. So while reporting the results, the numbers are often rounded to avoid reporting of insignificant figures. Example is an instrument measures to the nearest gram. The value is written as 12.345 kilogram. So you should not write 12.34500 kilogram. These two digits have no meaning. If you know that it is only accurate up to a gram. So how to round off these values? There are the rules for rounding of numbers. So you have to drop, let us say you have to drop these last digits. So the rules are, if the digit dropped is less than 5, the last digit kept is unchanged. That is, suppose you want to round it to the first decimal point, 6.42. So last digit, if it is less than 5, you say 6.4. So if it is less than 5, you say 6.4. This is how you can round it off. If the digit dropped is greater than 5, the last digit is increased by 1. Like if it is 6.46 instead of 6.42, then it becomes 6.5. So that is the difference. Now if it is exactly 6.45, so what do? If the digit dropped is 5 and the digit retained is even, then it is left as it is. For example, if it is 6.45, then you have to round it to 6.4. But if it was 3.5, then you have to round it to the next. So the last one should be even number. If the digit dropped is 5 and the digit retained is odd, then it is increased by 1. Like 6.35, you want to round it off to 1 decimal, you say 6.4. So if you remember this, and when you report your data, you will not make any mistake. So it will actually reflect the uncertainty in your numbers. So whenever you are reporting some numbers, that number, suppose you don't know the plus minus, that number itself, data itself should reveal the accuracy of your value. Okay. So when you have the measurements, the measurement may introduce different types of errors. And so you should know how to correct them. So the errors could be random. Random errors arise due to fluctuations in the measuring instrument, or even you are doing, your personal errors also come. Dependent operators will have their own different types of handling the equipment. So you introduce errors in that. And every instrument has got its least count. So you, like a balance has some least count. So you introduce the errors in measuring the data. So these fluctuations in the instrument or your signal to noise, so noise is like a random error. So how do you take care of that? Random errors affect the precision of a measurement. And so if you want to reduce the random error, you do multiple measurements. So for example, measurement of a mass of a coin in a weighing balance will introduce random error because there is a certain accuracy attached to the digits that are displayed. So the last digits, like in a balance, fluctuates randomly due to fluctuations in electric current or due to small air currents hitting the plate on which the coin is placed. So such errors are called noise and contribute to random error. Even if you are doing in an oscilloscope, and you are looking for some pulse, and always there is a noise in your baseline will be having some noise. So that baseline has some width, and that will be adding to the signal. So that is a random noise. So once you increase the signal, noise will be a small percentage of the signal. So these errors may be eliminated by taking a sufficient number of independent measurements. So the standard deviation will reduce as you increase the number of measurements. The contribution of noise to the average value vanishes for sufficiently large number of. That's why it's always advised that when you are quoting the error on a measurement, you have done sufficient number of measurements. Then the other one is the systematic error. And systematic errors arise due to the faulty measuring system. There is a fault of the system. You have, let us say, the standard weights are not standard. Your scale is not standard. The people who have measurement, they are having some bias in measurements. So all that will add to systematic errors. And the systematic errors affect the accuracy of measurements, whereas the random errors affect the precision of the measurements. So while the random errors can be minimized by repeated measurements, systematic errors cannot be minimized by repeated measurements. So instead of that, you have to do calibration. So you determine the accuracy of your system by doing the calibration. You take a standard and do the experiment with the standard, see how far is your measured value from the true value. So therefore, you have to always read user's manual before using any instrument, because every instrument can function within certain range of observables, or there may be conditions of, always we try to read the manual before using the instruments. Everywhere, do read the manuals whenever you are handling an instrument. Like this example which I narrated earlier, the Mulliken's measurement of the charge of an electron based on the movement of the oil drops under the force of gravity and an applied electric field, wherein you have to correct for the drag exerted by the air. And to correct for the drag, you should know viscosity of the air at that temperature. And in the case of Millikan, what happened that they did the measurement of viscosity of air at a particular temperature, but the experiment was done at some other temperature, and therefore the value of the charge of electron was lower by 1%, though Millikan claimed that it is accurate within 0.2%. So this is the kind of errors you can introduce if you are not doing the measurements in a. Then the kind of this experiment of Millikan is considered to be very, very accurate and precise, but even such experiments can have errors. So how do you improve the experiments? So particularly like in the case of hypothesis-driven research, sometimes a bias may come. And so bias is another systematic error that we introduce consciously or subconsciously. So bias is a general problem in hypothesis-driven research, and it refers to the action taken consciously or unconsciously by the experimenter, and these actions damage the validity of the experiment. So the bias will introduce a systematic error in your experiment. As I mentioned in the previous one also, like how many measurements you should do, like a survey also. When you are doing a survey, you have in your mind that this candidate should win. And how many people you have to evaluate, you start interviewing people. And after, let us say 1,000 people, you find that 600 people have said, yes, they will vote for that candidate. And you stop surveying more people. So you have biased. Means you got an output which suits your outcome, expected hypothesis. And therefore, This is a bias. Whereas if a priori you decide that I will interview 10,000 people to know about their opinion about their particular candidate, and you stop only after 10,000, irrespective of whether they favor or not favor the particular candidate. So this is the kind of bias. The researcher goes ahead with checking if the answer is in agreement with an expected value, and when it gets close enough, you stop taking data. So to prevent this, you have to a priori fix how many data you will collect, how many samples you will analyze, and then so that you are sure that you have not had any bias in deciding how many data you will analyze. Then in particularly, in medical research, there are a lot of this kind of biases may come. And so there are terms called single blind and double blind experiments. To take care of biases, there are different measures being taken by medical fraternity. So like, you want to test the efficacy of one drug over the other. Many times you say a new drug comes into the market and they claim that this drug is better than that drug. Now, how do you confirm that it is better than that drug? So they have to do a study and take a null hypothesis that the new drug is not superior to the old one. So this is the null hypothesis. And you have to reject the null hypothesis if you have to succeed in your experiment. Now, what you do, there is something called single blind experiment. That means you give this subjects receiving the treatment are not told whether they are receiving the old drug or new drug. So you are treating them with the two. So it is like, the old drug is like a blind. They are not knowing who is receiving old, who is receiving new drug, but you are having some blind experiment. Single blind means that people don't know, but the people who are administering, they are knowing. That is what the meaning of single blind. There are the people who are doing the survey, they are injecting the drug into the people. They are knowing whom they are injecting new, whom they are injecting old one. But people who are being treated, they are not knowing whether they are getting the old or new. But then when the people who are injecting, they know there is a risk of bias because unconsciously they will reveal to the patient that they are being given the new drug. So that unconscious signal they give to the patients, that might bias the outcomes. Then there is a double blind experiment, which is still better. In this double blind experiment, neither the subjects nor the people administering the drug know who is receiving what. So there is no bias. So they are not, the people who are injecting, they don't know who is receiving new drug, who is receiving old drug. So that is a very fair study. And that's why double blind experiments are favored. And there is another called the placebo effect. So this is again, when you are testing whether some drug is better or worse than taking nothing at all. Here we are comparing two drugs, but when you are like, these vaccines. So when the vaccines are being tested for their efficacy, some people are given vaccine, some people are giving a placebo. So the controlled group patients are given a placebo. The placebo is like a pill, like if you are testing a drug, then the people who are control group, they are given a placebo, means they are given a pill which is not medicine. It's not a real medicine. It is some other pill, some harmless ingredient. So that is called the placebo effect. And what happens now in particular case of testing the effectiveness of vitamin C in preventing cold, this can also introduce bias. The patients receiving placebo, this placebo was a sugar coated pills, and when they started chewing this pills, they realized it is sugar. So they came to know that they are not receiving vitamin C, but they are receiving the placebo. So this is also a kind of bias that can generate even in the placebo effect. Okay. So coming to this another aspect, many a times whatever we discussed, you are directly measuring one quantity and arriving at the conclusion about the hypothesis or not. Now, but there may be many times, in fact, most of the times you will find you do one measurement and you derive some other quantity from that. So for that, there are some rules of error propagation, and one has to follow this error propagation correctly. So for example, if you measure two quantities x and y with their associated errors, delta x and delta y, and you get a p, which is the either the sub addition x plus y or it is a subtraction of x minus y. So delta x and delta y are the uncertainties on x and y, and delta p is uncertainty on p. Then the errors are additive for plus addition and subtraction. So absolute errors are added square way. So delta p, the error on p will be square root of delta x square plus delta y square, irrespective of whether it is x plus y or x minus y. So absolute errors are added when you add the two quantities to get the third quantity. But when you do multiplication and division, like p equal to x into y or p equal to x divided by y, in that case, the relative errors are added. So the relative error on p, delta p by p square equal to relative error on x divided by the x value square plus relative error on y by y square. So delta p, if you want to find out, you say square root of delta x by x square plus delta y by y square into p. That is how you can calculate the error on a number which is obtained by multiplication and division of two quantities. And the same applies to multiple quantities also. Then the products of powers. So let us say p equal to x raised to m and y raised to n. Then here the delta p by p square is m delta x by x square plus n delta y by y square. So again, you can derive the error on the measured derived quantity from the measured quantities. Now, all these formulas have come from a general formula for error propagation. Those who are in physics and mathematics probably they will know it already. Like if you have a quantity measured, which is a function of multiple quantities like f of x, y, z, and so on, then the general formula for the error on this p is delta p square equal to del p by del x square, delta x square plus del p by del y square, delta y square plus so on. So essentially, these are the derivatives. So you have a function and the functional form is known. So you take the derivatives of that quantity with respect to the individual functions, partial derivatives, del p by del x, del p by del y, del p by del z, and so on. And these are the uncertainties on x and y and so on. So this you can apply to all types of formulae, addition, subtraction, multiplication, division, or even exponential power. So everywhere, particularly in logarithm, it becomes very useful to use this formula. So all these formulations are used for propagating the error on your quantities. I have just given one example on how to determine the error on density. So you determine the density of a coin by measuring the mass and the volume. So if you density rho equal to mass upon volume. So you measure the mass, you can weigh it in a balance, measure the volume. For measuring the volume, the coins are very thin. So you can use a ruler to measure the diameter and thickness of the coin. So the diameter of the coin D and thickness of the coin T. So let us say diameter is 18.5 plus minus 0.25 millimeter. Visually, you can read this data. And you use the same ruler to determine the thickness 1.25 millimeter plus minus 0.25. So your ruler has got this uncertainty. So volume equal to pi r square h. So you have determined the D and T. So you can determine the D square. You can determine D square into T. So that is how so when you propagate the errors, this is the D and this is the T, and you have to propagate the errors on the D square T. Same formula like shown in the previous slide. So you get the d square t 428 plus 185 mm cube. And then you multiply by pi by 4, because d by 2 square, so pi by 4. You get, so 336 plus minus 67 mm cube. And you, in centimeter cube, 0.336 plus 0.067 centimeter cube. And mass you have determined, let us say 2.529 plus minus 0.001 gram. So you have rho density mass upon volume. It becomes 7.53. Again, the errors you propagate mass upon volume. And so you get final results 7.5 plus minus 1.5 gram per centimeter cube. Now you see here why this has been rounded, because the error is very, very high. On 7.5, you have got 1.5 as uncertainty. So why this uncertainty has come? Because uncertainty in T. You see that the thickness of the coin is very uncertain. 1.25 plus minus 0.25. That is almost 25% uncertainty. That is what is reflected in the final density. So the large uncertainty in thickness determines the overall uncertainty in density. A single quantity in the formula, if it is erroneous, then your entire, however accurately you determine the mass, your measurement will not be accurate. So having much smaller uncertainty dominates the final result. So in the formula, whatever quantities you are using, all of them should have lower uncertainty. A single quantity can spoil your measurement. So how do you improve the measurement of your values? Some important outcomes. One is that if you want to reduce the random error, do the measurements maximum more times. So the standard error of mean is given by standard deviation upon root n, where n is the number of measurements. So n equal to s upon delta x square. So suppose you recall that experiment on flipping a coin 100 times, and you got the delta x as 0.05 with a standard deviation of 0.5. So you got 0.46 plus minus 0.05. Suppose you want to improve the error from 0.05 to 0.005, then n will be 0.5 upon 0.005, and so you get 10,000. So that means if you flip the coin 10,000 times, your data will be close to 0.5 mean value. So it is very difficult to do 10,000 times, and that is where you have to optimize your number of sample size and so on. Similarly, so for random error, you can increase the number of experiments. For reducing the systematic error, you calibrate the instrument carefully or design the experiment with new and more accurate measurements. For example, you use the ruler to determine the thickness of the coin. Instead of if you use a vernier caliper, you will get the thickness of the coin very accurately, and you can improve upon the density of the coin. So these are the kind of things you have to take. Then many times, when doing the measurement, if you are not very careful, you may get one or two results which are not a part of that measurement. They may be outliers. So how to detect the test for the outlier? There are two tests. One is the Q test, Dixon's Q test. So suppose you have suppose you have 10 measurements, mass of a coin or anything, and one of them, while noting down, you made a mistake. So that could become an outlier. So to test that outlier, you arrange the measured data in increasing order, let us say, from lowest to highest, x1 less than x2 less than x3, so on. So there are n data, arrange them in the increasing order. Or you can do other decreasing order also, whatever it is. And you define a quantity called Q. So suppose x1 is the outlier. Then you define a quantity x2 minus x1 upon x1 minus x1, xn minus x1. So this is the range of the value, highest and lowest. And this is you are comparing the lowest with the previous one. for x1. If you are suspecting that x1 is the outlier, take this value. And if you are suspecting xn is the outlier, you do xn minus 1 means the adjacent data difference minus the range value. And then you compare the q value with the critical value of q, which is given in this table. So critical value of q is for different confidence level, 90%, 95%, 99% for the n number of degrees of freedom. So how many measurements you have done. And from there, you find out. So if the q is more than q critical, then it is an outlier. So whatever q you get, in this case, if q is more than q critical, x1 is outlier. In this case, if q is more than q critical, xn is outlier. So that is how you can reject the outlier. So that instead of blindly rejecting a value, you do this q test and then say this value might have some error. You might have made some mistake in noting down this error. Then another way of rejecting the outlier is Grubs test. And it is actually like that t-test. So here you assume that the values follow a normal distribution, but one of them may be an outlier. So the values are again arranged in an ascending order like A1, A2, A3 to AN. And here now you use the mean value and the standard deviation from that measurement to deduce a quantity called T. So it is like the T value in the t-test. And you define as AN. Now AN, suppose you suspect that AN, the last value is outlier. You calculate AN minus A bar upon S. So the null hypothesis is that AN belongs to this set. This is a part of this. This is not an outlier. So you calculate this T value and compare with the T table, and you see if T is less than critical value, then hypothesis is tested, means this is not outlier. But if it is more than critical value, then you say it is a outlier. So if the suspect value is A1, then you use T1 equal to A bar minus A1 upon S. If suspect value is AN, you say AN minus A bar by S. So that is how this is another way of doing a test to reject the outliers. It's called Grubs test. And this is that value of Grub statistics. Again, for number of measurements and the confidence level, these are the value of the T, which you can compare. These are the critical values of the T value, whatever I showed here, and you can compare with the critical value. Okay, so finally, to the last slide of this, quality control measures are very, very important whenever you are doing any measurement. So there are two terms called quality control and quality assurance. So quality control means, whatever you are measuring, when you are doing some data, you're getting a value. Suppose you do some measurement, then you have to reject some impurity concentrations in some samples. That itself is a part of the quality control. You have to do some test on a consignment, or some product is coming out. How good is the quality? You have to do a quality control check. And quality assurance is that you have to give an assurance to the people whom you are supplying that this is how you have established the quality control of your products. So quality assurance is the set of procedures that you do in the laboratory routinely to give a confidence of the reliability of your data. Whereas quality control is for your sample that you are analyzing about the sample, how good is the sample quality data that you are, it's part of quality control. So for quality control, you measure the use of laboratory standards, measure the background, analyze duplicate samples or multiplicate samples. You have some control charts, standard peak stability, how stable is your peak if you are doing some voltage measurements, and you use the reference materials. Whereas for quality assurance, you calibrate your equipments, and that is your assurance to the people that yes, you are calibrating your equipment, so your data is reliable. You are using calibrated standards. You have an internal audit. So there is a audit of your all procedure, SOP, instrument done. There is, you participate in the interlaboratory comparison exercise, ILC, to show to the world that your data are reliable. You train your personnel for the operations that to do, and you use the standard methods like ASTM methods or well laid down procedures you follow as a part of your quality assurance. So any people particularly who are doing the experiments, measurement of values, so they have to have both quality control and quality assurance in place to establishing, particularly, nowadays you will find ISO 9001, ISO 14001. What are those things? They have certain standards. They pass those quality checks so that you get the certification based on these tests. So that is the part of the quality control and quality assurance. You say our company is ISO 14001 certified. So that's all I have to say today. Thank you very much. And again, I want to remind all the students that, as I mentioned in the beginning, many of you might have joined late, that with a view to record your presence, not only the presence, to later on to evaluate the assignments and for examination purposes, we need to know the CI or OCC wise names, details of all students. And for this purpose, you have been given a Google form link by our friend here in HBNI. In the chat box, you may find that Google link. So there you have to click on that link and write your name, email address, mobile number, enrollment number, and name of your CI and OCC. So this you have to fill by today or tomorrow so that we know how many students, who are the students from different CI. So this one, I'm sure you are going to take care in your subsequent today or tomorrow. Okay. Now let me see if you have any questions. Yes. So this is the link, https forms.gle. So that one you can click and write down your name and all the details which I mentioned just now. Okay. So there is one question in slide number 13. The standard deviation is given as 3.11 E minus 3. Shall we correct it? Yes, you are very right. So you have to round it off using the formula that I gave next slide. So use that. Okay, so yes. In slide number 14, the rounding off when the last digit is 5, choice of even or odd looks arbitrary. This is the standard practice that if the last digit has to be 5, then you choose. If the previous one is even, you retain it. The previous one is odd, you go to the next one. So it has been followed in mathematics, in rounding off, in all the practice. This is the standard practice has been followed. That's what is there. It looks to be arbitrary, but you have to follow that pattern. Enrollment number option is not present in the form. Please clarify. Okay. I am also not very much aware of this. So if it is not there, you don't worry about that. Your name and mobile number, email address, name of the CI. In fact, this enrollment number, I only suggested maybe by that time they have already created. It got disconnected. So you can try again. You can copy this link in your mobile and later on also do it. And you will also get a chance to do it tomorrow. We will find enrollment number from our site. Enrollment number has not been assigned to this year DDFS batch number. Don't worry if it is not assigned. You write your registration number as you are telling. Can you provide the link again, please? I cannot provide, only my friend. Yeah, this is the there. When we say the measured value and true value, where one gets the true value, which is not generated by the measurement. Yes, you are very right. You don't have the measured value. And yesterday, if you recollect, then that one is that the true value is the standard value. When you do measurement, you are running a standard, then that standard value is the true value, which has been arrived at by interlaboratory comparison, or the people who have generated the standard, they quote that number. So with that you can compare. But if you don't have a standard for your sample and you are doing measurements, then you do multiple measurements, and that itself you have to take. I gave that example in the previous one, that how do you arrive at a value by multiple sample analysis with a large sample to go as close as possible to the true value. What is ILCE? ILCE is inter-laboratory comparison exercise. You see, if you want to generate one standard, then at least 20 laboratories have to participate in this exercise, because the multiple number of analysis, then you can generate a standard. So in this ILC exercise, more than at least 20 laboratories participate, and that data of 20 laboratories. So you have 20 means. They are analyzed statistically by the formula which I discussed last Monday. And then from that you get a mean value. That is so you get a sampling distribution of mean, and then then you get the standard error of that mean. So that becomes the reference value for others who will use that sample. So that is how the interlaboratory comparison exercise is done to generate standards. They are called certified reference materials. Okay. So it looks there are no further questions. So I will stop here, and we'll meet tomorrow. Okay. The results from ILCE has to be necessarily precise but not accurate. You are very right. See, the systematic error gets introduced by some biases. Now, if 20 laboratories are using different methods, it is very unlikely that all of them will be biased. So, it can happen that out of 20 laboratories, one or two may have faulty measurement practices, and therefore that is why this more than or equal to 20 laboratories participate. So at least majority of them will be having a fair SOP for measurement, and so the chances of bias are very less. And that data, then so there also you reject the outliers. That Q test becomes very important when you have an interlaboratory comparison exercise. So you do the Q test, reject the outliers, and the remaining one you perform analysis to find out the population mean. You can use that data. Enrollment number option is not present in the form. Don't worry, you write other details. There is no problem. Okay. Okay. So we will stop here, and we'll meet tomorrow, same time. Thank you and bye bye. Okay, there was a question. Can I